It's a pleasure and a bit of an intimidation to speak in front of such an august group. And I will say that I have known our two previous speakers for quite a long time. I sort of realized as I was watching the beginning of the session this morning that I have learned from Carl and from Nick, as well as from others, the value of complex systems approaches. But I have never understood that crap at all. It's taken me a long time to get to self-acceptance on this. And I think I finally reached that, and I can sort of summarize it very briefly. People like Carl and Nick, I view as producers of knowledge in the realm of complex systems. And I like to think of myself as a consumer of that knowledge. So if you think Steve Jobs was a genius for designing this, I agree with you. And I can use it even though I have no idea what's inside of it and how it works. So you guys are my Steve Jobs, and I hope you don't mind the way I use your phone. This is all a prelude to the fact that when I was invited to give this talk, one of the first things I thought about doing was talking about dynamic systems and complexity as it relates to posture and aging, and then I looked at who else was speaking, and I thought that would be a very foolish thing for me to do. So I'm actually taking a somewhat different approach here. I'm going to accept that these guys know much more about that stuff than I do, and you will see some references in here to complex system stuff, but again, I'm just using the variables that people like this developed. Postural activity keeps the body's center of mass above the base of support. When you stand up, if your center of mass is above your feet, that means you're standing, and if your center of mass gets beyond the boundary of your feet, that means you're falling. Postural activity, of course, is organized to keep us from falling over. That's, we don't like to fall, and that's okay for babies in diapers, but the older you get, the more you don't like to fall, and you really do want to keep your center of mass over the feet. For many, many years, this activity, the activity of keeping the center of mass over the feet, was more or less assumed to be the primary object or task of postural control. That is to say, when you stand up and you contract the muscles in your legs that in fact displace the center of mass, that the sort of purpose or the intended outcome of that primarily was to keep you from falling. In addition, those control actions have traditionally been thought of as being reflexive or automatic, consisting of motor programs or neural strategies or whatever. Over the past 20 years approximately, there have been some questions raised about both of these ideas, not in the sense of replacing them necessarily, but just in thinking about, well, maybe there's a little bit more going on or things are working a little bit differently than we may have thought. There's increasing acceptance of the idea, for example, that postural control is not a set of simple reflexes. That idea has advanced far enough that it's not really very controversial anymore. But equally important, and this is more the focus of my talk this morning, postural control actions are now known to change in a sort of situation-specific manner in ways that are not obviously related to the avoidance of falling. There's a lot of things that you can do with your body that will keep you from falling. And given that a lot of things that you can do with your body will keep you from falling, there's not a falling-related reason to choose among them, and yet we choose among them. And so there's some interesting questions emerging about, well, why do you do it this way instead of that way, given that both ways keep you from falling? Many studies have shown in a wide variety of settings that postural control actions are influenced by concurrent, what I refer to as suprapostural activity. Some remarkably simple things, some really remarkably simple things. One thing that most people know, even casually, is that the way your body moves is different when your eyes are closed than when they're open. That's not news. What is a little bit more newsworthy is that your body sway changes when your eyes are open, depending on what you're doing with your eyes. So if you're looking at something as opposed to just staring off into space, there are reliable differences in the way your body's moving while you're doing those two different visual activities. Even remembering things influences the way your body moves when you're just standing there. This effect is a little bit more labile, but it's there and it's reasonably well documented. Even just thinking about things, this is kind of almost cryptic, but yeah, the stuff that goes on in your head is correlated with the changes, situation-specific changes in the way your body moves. These kinds of effects, when they first began to be documented and observed, gave rise to the hypothesis that postural control competes with simultaneous non-postural or suprapostural activities for what's commonly called a central pool of processing resources. This is the classic dual task view, and in this view, postural control will tend to interfere with suprapostural activity, and vice versa. And the sort of grand hypothesis there was that when you stand up and do something else while you're standing up, that if there's sufficient demand in one or both of those tasks, that will cause you to have degraded performance in one or both of those things. How does this relate to aging? Well, it relates to aging, again, in a hypothetical sense, because one of the things we know about aging is that there are documented declines among even healthy elderly in certain cognitive functions. And that is often interpreted as arising from a concomitant decline in the hypothetical pool of central processing resources. That is to say, it's commonly asserted that older people have less stuff left in the tank. And to the extent that you have less stuff left in your tank, then when you are trying to do 2 or 3 things at once, that it will make them harder to get done. In the area of postural control and aging, a lot of studies have sought to confirm this classical model. It's a straightforward model, and it had a good intuitive basis. But the data, it turns out, have been quite equivocal. When people have, in a variety of labs all over the place, have given adults, and older adults in particular, these sort of dual task situations where one task is to stand up and the other task is to look at something or think about something or listen to something. It simply has not reliably been the case that there's been evidence for any kind of a competition between those tasks. And Wollicott and Shumway-Cook provided what is still, for my money, the broadest and most helpful review of all this stuff. They concluded that the effects of competition between postural and suprapostural activities for central processing resources, and I love the concision of this phrase, appear to be small. So a nice, clear hypothesis, but one that in fact has at best equivocal empirical support. So maybe that's not really what's going on. Maybe we should think about an alternative way of approaching this. So it certainly is the case that postural activity keeps us from falling. Yes, when you stand up, you are continuously contracting and relaxing various muscles that in fact displace the center of mass and in fact keep you from falling over. That's why you don't fall down. However, that's not all that is going on, because postural activity also affects the position and motion of the rest of the body, not just the center of mass, but all of you. As you sway back and forth, your center of mass, I should do it this way, as you sway back and forth, your center of mass is being displaced, but so is the rest of you, in particular including the thing at the top, which is your head. And that head, sometimes referred to as the sensory platform, contains the most sensitive and the most important of your sensory receptors for maintaining contact with the rest of the world, your eyes and your ears. And of course, the limbs and all the rest of it are going to be moved around too. So postural activity can affect the performance, in principle can affect the performance of suprapostural tasks, such as looking and listening and manipulating. And the sort of classic example is that you're standing there reading a book or something and somebody bumps into you and your eyes slide off the page and you stop reading. They didn't push your eyes or bump your eyes. They pushed your body and displaced your center of mass, but that also just, the head goes away and the eyes slide off the page, and you know what? You're not reading anymore for a moment, whether or not you fall down. This is important because the performance criteria for these suprapostural tasks are qualitatively different from the performance criteria for postural control. The performance criteria for postural control is my center of mass is above my feet or it's not. I fall over or I don't. It's essentially a mechanical criterion. And look, my postural control is successful. How can you tell? Because I'm standing up, not falling down. Okay? Well, if I'm standing up and reading, yes, my center of mass will be moving around, but I don't care about that in terms of my success at reading. You know, again, if you bump into me and my eyes slide off the page, I'm not going to say, oh, darn, while I was reading, my center of mass moved. I'm going to say, crud, I failed to read what I wanted to read. I didn't understand it or whatever. You look in the classical reading literature, what makes a good reader, reading is defined in terms of things like reading rate and comprehension. Reading rate and comprehension differ qualitatively from the position and motion of the center of mass. And yet, the position and motion of the center of mass can affect them both. What this means is that postural activity might be controlled to satisfy simultaneously both the postural criterion to avoid falling and the suprapostural criterion, that is to say, in the case of the example I'm using, to facilitate reading. And as it says down at the bottom, in this view, variations in postural activity can facilitate the performance of suprapostural tasks. So rather than suggesting that standing up and chewing bubblegum, to use everybody remember President Ford? People suggest that you couldn't walk and chew gum at the same time. Well, and the idea, hey, the intuitive idea behind that was there's some difficulty in putting these tasks together. Well, rather than going with that sort of President Ford hypothesis, if you will, I'm suggesting essentially the opposite, that putting the tasks together may actually lead to facilitation of at least one of them and possibly both. And in fact, Nick just a minute ago showed us something that was entirely compatible with that in the case of walking. If you walk and do something, you wind up with an improvement rather than a decrement. I'm going to describe a couple of paradigms that are fairly widespread that have provided some information about this sort of stuff, and I picked these two paradigms in part because I'm involved in both of them, although I'm not the only person or lab. So these things can be really, really simple. So you have a person standing up, you have some technology that allows you to measure how they move, and you put something in front of them for them to look at. In this case, they're either looking at a blank piece of paper, which is not very demanding of the visual system, or they're looking at a block of text and they're reading through the block of text and searching for every instance of the letter R and counting up the number of R's that they see. This is just a way to get them to read where the scientists get some sort of data about what they did. Effectively, it's just the difference between staring at a blank piece of paper and reading. So you have unperturbed stance. You have two suprapostural tasks, the one at the blank target that we refer to as the inspection task, and when you're looking through for target letters, we call it the search task. Does it have effect on postural sway? Yes, it does. Here's postural sway when people are looking at a blank piece of paper, and here's the same person a few seconds later, standing in the same place at the same distance from the target, but now there's looking through a block of text. We're not, by any means, the first people to show effects of this kind. We're simply placing a different interpretation on them. The interpretation that we place on this is that when you are staring at a blank piece of paper, it really doesn't matter very much where you point your eyes or how stable your gaze is. But if you're reading, those things matter a whole lot. So when you're staring at a blank piece of paper, this amount or this type of postural sway is not going to hinder your performance of the visual task. When you're doing reading, if you tone things down, that may facilitate the performance of the reading task. Here's the second general paradigm. This one's one that shows up a little bit less in the experimental literature, but which has a lot of intuitive power for folks, which is what I refer to as the Grand Canyon effect. If you've been to the Grand Canyon or at the top of a tall building, if you go to the observatory platforms on the Empire State Building, or the one I like is the CN Tower in Toronto, because they have a glass floor that you can stand on and look down. A lot of people don't like to do that. If you stand at the edge of the Grand Canyon, if you stand in one of these high places, a lot of people experience vertigo. In spite of the fact that it's physically impossible for you to fall. So there's a whole literature about fear of heights and that kind of stuff. But there's, over and above the vertigo, there is an effect on the control of the body. And that is that in a wide variety of situations. So here we have this is just a cute little picture of it. So here we have a person who's either looking at something that's very close to them, or looking at something that's at a moderate distance, or looking at, this is an adjacent building. This is done in an outdoor setting. Bless and his colleagues were the first people to do this back in 1980. What they did, the reason it took so long for this to be done is that everybody took it for granted. And it took a long time for some scientists to say, maybe we actually need some data on this. What Bless originally did was he measured people's postural sway while they stood on the ground floor of a building, and consequently the surroundings were very close to them. And then he took them up on the 10th floor and put them on a balcony where they could see off to the horizon. So the only difference was just how far away was the stuff they could see. And what he found was that people swayed more when they were looking at the horizon, and they swayed less when they were looking at things that were close by. And we found the same thing. We started doing this kind of research a few years ago, and verified this, and have done similar things over the years. So when you look at a nearby target, you don't sway very much, and when you look at the horizon, you sway quite a bit more. I could go into the explanations for this, but for reasons of time, I won't do that. I'm just ask you to accept this as a pretty widely replicated effect. Well, then you get into aging. So I'm going to take the two paradigms that I just described for you were pioneered with younger adults, and now we're going to take them each and look into aging. So one of the things we know from countless studies, and Nick mentioned it, is that older adults, even healthy older adults, sway more than younger adults. This is an absolutely classic finding, and it's very, very widely interpreted as implying, as evidence of a decline in the control abilities of older adults. So older adults sway more. Classically, this increase has been interpreted as a deficit. They sway more because they can't help it. There's a very deep assumption that given the choice, we would all like to sway less. And that if we sway more, that's going to be because we can't help it. Well, let's look at this question, let's look at this effect in the context of variations in these suprapostural tests that I've been talking about. So we did a study a number of years ago with Marcos Duarte down in Brazil, where we simply replicated this paradigm, comparing older and younger adults. So you look over here, the older adults, as opposed to the younger adults, sure enough, the older adults sway more. Okay, each one of these bars is higher for the older adults than the younger adults. Yes, indeed, older adults sway more. But the main thing was that we were interested in whether and how the older adults might modulate their posture based on the visual tasks that they were doing. And this graph is a little bit hard to interpret, so I'll point it out for you. So here again you have the younger adults, and these are two different conditions in which they're looking at which they're looking at the blank target, and these are two different conditions in which they're doing the reading task. And you see blank target reading, so sway is decreased when they do the reading, and here's blank target reading, and the sway is decreased when they do the reading. And lo and behold, even though the older adults sway more overall, again replicating an absolutely common finding, nevertheless, the older adults show the same ability to modulate their sway based on the visual tasks that they're doing. An overall increase in sway, but no decline, no measurable decline here, none, in their ability to modulate sway based on the suprapostural activity. So maybe, that's what this question mark is about. Now let's look at this in the context of the second paradigm, where you're varying the distance of the visual target. So in an outdoor setting, we sort of emulated the original work of Bless from the early 1980s. We didn't use the floors of a building, but we did this in an outdoor setting. We had targets that were half a meter away, 3 meters away, and 100 meters away. We looked at two different aspects of the data. We looked at how much people swayed the classic sort of measures that Nick was talking about at the beginning of his presentation. And then separately, we looked at the one measure of the temporal dynamics of sway. In terms of the magnitude of sway, we get the classical effect. And the thing to point out about this is, so this is sway forward and back in the AP axis and sway side to side. The effect here is in the AP axis. This is a main effect, okay? A main effect meaning it applies equally for the older adults and the younger adults. So just as we have here, the older adults showing the same ability to modulate posture on the basis of visual tasks as the younger adults, we have the same thing here, that the older adults are showing the identical ability to modulate their posture based, in this case, on the distance of the visual targets. So no difference between older and younger adults in the spatial magnitude of sway. When we looked at the temporal dynamics of sway, in this case we used a metric called multifractal detended, I can't say it. Carl, could you say it for me? Multifractal detrended fluctuation analysis. Yeah, well, it goes with the long journal names. And here you have something that is a difference between younger and older adults, but a difference in exactly the opposite direction that we might suppose. In this case, the younger adults are not showing any variation, any reliable variation in the temporal dynamics of their sway as a basis on the basis of target distance, but the older adults are. This is the first evidence that I'm aware of that you have an aspect of a very subtle and task-specific aspect of postural sway that is apparently functional in older adults, but not in younger adults. And it really, I mean, it's a lone result at this point, but it certainly underscores this idea that older adults are, while they're swaying more overall, are not necessarily losing control of their bodies in terms of postural sway. I put that phrase in there, in terms of postural sway. We'll get back to that later on. Well, all of these things, again, you can, so this is a paradigm using unperturbed stance. And this is a paradigm using unperturbed stance, but as many of you know, we also have paradigms in which we study stance in cases of perturbation. And in fact, Nick was showing you some of this stuff with the virtual reality things where you're giving people these visual motions and seeing what they do with it. Nick's, the virtual reality case is the third one that I didn't put up here. What I usually use is real reality, what's known as the moving room paradigm, where you put people inside a big box, they're standing on the floor, and you move the box around them, and the visual motion that results from that can produce very, very dramatic changes in posture. Babies, you can knock them down. I think that's why they're wearing diapers in my lab, so that they can, it's padding. And adults, you can stagger them. You can literally cause people to stagger simply with the photons. Here. And then one that's probably more familiar is moving platform posturography, where it's not a visual perturbation, but it's an actual physical perturbation of the basic support. Both of these things, both of these methods, and the VR method that Nick uses, will make you sway. And they'll make, you know, depending on the conditions, they'll make you sway a whole lot. And the point I want to make about this is that at least some portion of this increased sway is adaptive. The moving room, the common interpretation of the moving room is that the nervous system interprets the visual motion as the body falling over. Well, if you feel that you're falling over, you need to move, and you probably need to move a lot to recover from that. So again, if I bump into you, yeah, I'm going to perturb you and cause you to move in a way you don't want to, but to recover from that, you're going to have a big movement. That sway is adaptive. The same thing is true of, again, a large portion of the increased sway that's observed in the moving platform posturography paradigm. So this statement needs to be changed a little bit. Say, in both paradigms, a large portion of this increased sway is adaptive. Well, those are laboratory situations where the scientist is using perturbations that can be generated in the laboratory. There are some limitations to perturbations that can be generated in the laboratory. In the lab, perturbations tend to be simple. typically in one axis. They tend to be small. When we're talking about a moving room or moving platform posturography, the magnitude of the perturbation is on the order of centimeters. And they tend to be very brief, commonly in terms of seconds or maybe a couple of minutes. And they have these characteristics in part because the technology they have in the laboratory can't do anything else. This gets us to sea travel. In sea travel, you're on a ship, the ship is on the sea is moving. Sea can move a whole lot, and that means that the ship moves a whole lot. In sea travel, you have perturbations that are complex. They occur in 6 degrees of freedom rather than 1 degree of freedom, and they're aperiodic in all 6 degrees of freedom. They're complex in really serious and meaningful ways. They're large. Ship motion can be on the magnitude of meters, and very commonly is. And they last a long time. They last as long as you're on the ship, 24/7. As long as you're out there, that ship is moving. The motion varies over time with the weather and the waves and so forth, but it doesn't go away. Humans have been going to sea for at least 30,000 years. At least 30,000 years. This is one of the most ecologically valid situations that we could use for study. Not only is there a long history there, but you have this remarkable thing. You know, how many of you do research in which the subjects pay to be in your study? Each year, more than 15 million people pay to be exposed to the challenges of ship motion. They pay for that. That means, all of this stuff together means that if a scientist can get onto a ship with some experimental technologies and techniques, there's an opportunity there to look at stuff that may be interesting. And we've had these opportunities and we've taken advantage of them. And if you've been on a cruise, oh my goodness, thank you. If you've been on a cruise, then you know some of this. I'll try and get through some of these. Could we see the first video, just a little bit of it?
Six knots of wind.
There we go. All right, so ship motion forces, it compels global change in perceptual motor control. This is a fancy way of saying people have to get their sea legs. And again, if you have experience on a ship, you know what that means, at least qualitatively. Well, we've begun to study these changes in terms of standing postural control. And if you place people on a moving surface, in this case a ship, and you move that surface in 6 degrees of freedom over a range of meters, and you do it for 24/7, you're going to see some change. You are going to see some change. This is a within subjects comparison. That is to say, this is one individual standing on a force plate at the dock, and this is ordinary postural sway. And this is the same person standing on the same force plate on a ship in, I want to point out, in mild weather. This is not during a storm. So the fact of being on a moving surface, well, I don't need to tell you about it. You can see it. Okay.
How much of that variability is due to the motion of the ship versus the motion of the person?
We'll take questions later.
Despite this overall increase in the motion of the body relative to the ship, young adults, and these data for young adults, retain the ability to modulate sway to facilitate suprapostural performance. Here's the exact same looking at a blank piece of paper versus reading a block of text. So that stays there. Okay. We've also done the distance thing. looking at near targets versus looking at the horizon. We did this on a ship that was at the dock, so there's no ship motion here. This is in the Bahamas. Yes, I suffer for my science. Here we have people standing on the deck of the ship looking at a near target. Here they are looking at the horizon. Here's the same deck, the same ship, the same objects, the same everything. Now we're out at sea. You can see the wake, and we're looking at the near target versus the horizon. When you are on, when the ship is at the dock, people sway more when they look at the horizon and sway less when they look at the near target, just as they're supposed to do. That's the classical result. 24 hours later, when you're out at sea, everybody sways more. The ship makes you move, but you have flopped over this effect, and now people sway less when they look at the horizon, and they sway more when they look at the near target. Excuse me. You get to age. 15 million people a year pay to go on ships. Fully half of those are 55 or older. I submit to you, consider relative to the theme of this meeting, that going on a vacation cruise as a retired person is active aging. Yeah, there's some self-selection here. However, a 3-meter swell, that is to say when the surface you're standing on is moving up and down 3 meters 24 hours a day, a 3-meter swell is a challenge for anybody. I don't care who you are. And I would show you a video of that, but maybe later. We have done a couple of studies looking at aging on ships at sea. I'm going to give you a little bit of qualitative data and then some quantitative data as quickly as I can. We went on a so-called retirement cruise that included 500 older adults, and just as our walking around and living on the ship with these people, there were people there up into their 90s. There were people that used canes. There were people that used walkers. There was a blind man, for heaven's sake. We were on the ship for 2 days. We did not see anybody fall down ever. And we did not see people stagger. These are people who are going through the line in the cafeteria carrying their trays with lunch. The trays all got to the tables, and everybody had lunch. So we saw no falls. Here's some qualitative data. At the dock, we asked people a couple of simple questions to rate their subjective bodily stability and to rate their awareness of ship motion. When the ship is at the dock, they feel really stable, and they're not aware of any ship motion because the ship isn't moving. You take them out to sea, the subjective bodily stability drops off, and then it recovers on the second day. The awareness of ship motion goes up, and it modulates a little bit. Both of these are pretty good indicators of getting your sea legs. What's really, what was of most interest to us is that we also had people do a Romberg task. That is to say, heel to toe, and you count the number of seconds they can do that. And when the ship is at the dock, when it's not moving, well, that's what you can do. You can do what you can do. You take it out to sea, roll motion is a lot bigger than pitch motion. And so when you're facing the bow, you're going to have all that roll motion. And when you're facing sideways, you're going to get something different. So Romberg is pretty good here. It really plummets on the first day at sea when you're facing the bow, not so much when you're facing the side. And then here again is people getting their sea legs. It turns out that these data right here correlated with the subjective stability numbers. Only when facing forward was there a correlation between what people could actually do and how they felt. On the same cruise, here's one of our subjects. We had these folks look at a nearby target versus look at the horizon. We did not find an effective target difference on the spatial magnitude of sway. Not a replication of what has been found with younger adults. So yeah, there can be differences with age. On the other hand, target distance did affect the temporal dynamics of sway, as is shown here. Some conclusions. Yes, older adults sway more. You don't need me to tell you that. But they retain the ability functionally to modulate their sway, to facilitate the performance of suprapostural tasks. To me, this is one of the real big findings in this area in recent years. This combination, the fact that older people sway more and yet they can still functionally modulate their sway, poses some puzzles. Since they can sway less, when you have them read, they sway less. Since they can sway less, why do they typically sway more? Why do they sway more? Maybe it's not because it isn't because they can't help it, because the data show that they can help it. So the general tend to sway more has to have some other explanation. And the real big issue here is how does all this stuff relate to the risk of falling? Because people don't really care very much about standing body sway and aging. They care about how that stuff may relate to falling down. And the classical assumption is that more sway means more falling. But if more sway is not a deficit, then there's some questions, maybe some new questions about that interpretation. The relation between falls and the spatial magnitude of sway is more complicated than we thought. And to resolve these puzzles, we're going to need some different, I claim, this is my claim, we're going to need some better, and in particular, some more functional assessments of stability and posture. So stability and stance may tell us something about stability and falls, but if and only if we have functional measures of stability and stance. And I thank you for your attention.